Welcome back to Calculus 2. In this lecture, we're going to introduce another integration method called trigonometric substitution. And despite the name, trigonometric substitution, the integrals we'll be learning how to evaluate have nothing to do with trig functions. Our previous lecture was how we addressed evaluating integrals of trig functions, what we called trigonometric integrals. The integrals for this lecture for trigonometric substitution are entirely different. All right, so now that we're kind of getting into our Calculus 2 course, it's a good time to review the integration methods that we've kind of covered so far. We have the first one, substitution, arguably the most important integration method. And then a close second, some would even say maybe more important than substitution, but I put it at a close second, is integration by parts. Now, most recently, when we covered trigonometric integrals, we took our time to make sure that we see trigonometric integrals are a special case of substitution. It's pretty much regular U substitution with some trigonometric Pythagorean identities thrown in. So think of trig integrals not as a new integration method, but a familiar substitution. All right, well, let's take a look at an example here, the integral of the square root of 1 minus x squared. Now, this function that we're integrating looks deceptively simple. This is part of what makes integration so much harder than differentiation. Functions might look rather simple and similar to other simple integrals, but they might be completely different. Now, I want to put on the screen an example that is similar to this that is very straightforward to evaluate. Let's say we have this integral with an extra factor of x inside the integral. This integral requires a straightforward substitution, u equals 1 minus x squared. And if you carry that out, the extra factor of x out front, that's going to be used for the differential du. Our integral on the left there lacks that factor of x inside, so our substitution for the integral on the left, u as 1 minus x squared, won't work since we don't have an extra factor of x to use for the differential du. That's what I was saying, what makes integration so much harder. Two similar integrals, but they're drastically different in the amount of work it takes to evaluate them. All right, so the whole goal for this lecture, to kind of just keep moving forward, is our goal is to eliminate the radical or square root. Now, we're going to try to get creative with how we're going to do that. So we'll kind of take our time during the intro here to hopefully kind of not just state what the trick is, but to lead into that. So this method that we call trigonometric substitution, it's a method to evaluate integrals involving square roots or radicals. Notice the integral on the screen there. There are no trig functions in it. So ignore the title. The title, trigonometric substitution, is telling us something about the type of substitution we'll make. The integrals we're evaluating involve square roots and radicals, not trig functions here. All right, now let's take a look at how we incorporate this title, trigonometric substitution. The title gives you a hint, but let's kind of see where that title comes from. So let's think, for this radical, the square root of 1 minus x squared, how do we eliminate the radical? We can't simply just square this quantity. You can't square some quantity. You can only square each side of an equation. So squaring, that's not an option. Well, let's try to think about maybe some identities that look similar to the inside here. Now, I'm being intentionally vague because I'd like you to try to come to it on your own, but think, do I know any formulas, equations, identities that fit the structure of what's inside the radical? 1 minus something squared. And the something, maybe you thought of it, that looks like one of our manipulated Pythagorean identities. 1 minus sine squared equals cosine squared. Now I realize it's maybe a bit of a stretch. The integral involves x. 1 minus sine squared of theta involves trig functions of theta, but they both fit the form 1 minus something squared. So what this is hinting at is, well, maybe if we try to use this identity in some way, we can kind of rewrite the inside as cosine squared. A square root of something squared will cancel out, thus eliminating the radical. Now, how do we actually go from the radical expression in x to trig functions? Well, we make what's called a trigonometric substitution. X equals a well-chosen trig function. And here, to connect it to our Pythagorean identity on the screen, we're going to make the trigonometric substitution x equals sine of theta. All right, let's see why that works. We're going to make the substitution replace everywhere in that expression x with sine of theta. Right now, we're going to look at how the radical gets eliminated. So let's plug that in. Replace x with sine of theta, and since it's x squared in the radical, we get sine squared of theta. Just be careful with your notation for powers of trig functions. And then the key to what eliminates the radical here is we use a Pythagorean identity, the one on the screen previously. Cosine squared equals 1 minus sine squared. What that allows me to do is replace that complicated inner expression, 1 minus sine squared, with the squared quantity, cosine squared. And hopefully you can see here how the radical gets eliminated. We have a square root of something squared. So at the end here, this simplifies to cosine of theta. There is no more radical. That's pretty much how we implement our goal, how we eliminate the radical. There's some details missing. We were talking about trigonometric substitution. You might expect something about differentials to come into this, like we did with u substitution, u and du. So there's a lot more to this, but this is how we're going to eliminate radicals. All right, let's go ahead and get into the rest of this lecture. This is just the intro phase. What I want to point out before we advance is we start with an integral involving square roots or radicals. And what this new technique called a trigonometric substitution does is it converts an integral with radicals to a trigonometric integral. And just think, what did we learn about most recently? How to evaluate trigonometric integrals. So there's both kind of a good and bad thing about this. This is basically saying this new type of integral with the appropriate conversion, a trigonometric substitution, we can rewrite it as something that we already know how to evaluate, a trig integral. Now the bad thing about this is all the possible cases for trigonometric integrals start to become a lot. So there's a large amount of baggage going into evaluating trig integrals. So before we kind of get into the rest of this lecture, if you feel at all uncertain on anything related to trigonometric integrals, go back and watch our previous lecture to kind of build your foundation for that, since we're going to be relying on that heavily in this lecture. All right, with that out of the way, we'll recall that as we go. Let's point out another important idea. And even though we're going to be focusing on integrals involving radicals and square roots, not all integrals with radicals require this new technique called trigonometric substitution. Now there's 3 examples on the screen here. The beauty of doing a recorded lecture like I am with you now is you can pause the video, which I'd like you to do, and give yourself as much time as needed to work out these integrals. Some of them are substitutions. One of them is a basic antiderivative. We'll check in a few minutes. All right, now some of these, the first and second, should be straightforward substitutions. The third one is actually a basic antiderivative. No integration methods are needed for example 3. So for the first and second examples, you actually make the same substitution, u as 1 minus x squared, and we have the results on the screen there. These should be pretty straightforward if you feel pretty solid with substitution. Now the third one is not difficult, but it's just tricky. It might have been forgotten from when you last learned about derivatives of inverse trig functions, which was kind of maybe around the halfway point or a little bit before in your Calculus 1 course. All right, since the derivative of sine inverse or inverse sine of x equals 1 divided by the square root of 1 minus x squared, we can flip that around to get this antiderivative statement. The integral of the square root, or 1 divided by the square root of 1 minus x squared, that comes out to inverse sine. All right, so just keep that in the back of your mind. We'll recall that as we kind of go through this lecture and examples. But before we move on, let me show you some examples that involve radicals that a substitution, at least that I'm aware of, would not apply, be applicable with. All right, and the two integrals, which we'll evaluate eventually, here I'm not aware of any straightforward substitutions that work, but the technique we're learning about now, trigonometric substitution, will work. All right, and notice with all of those 5 different integrals on the screen, they look similar. There's square roots involving 1 minus x squared, square roots with x squared minus 4 inside, powers of x. Unfortunately, there's no kind of general ways to evaluate integrals. That's what, again, makes integrating so much harder than differentiating. All right, let's get to some of the details. Just to kind of focus our lecture for the simpler examples within part 1 and 2 of this lecture, we're going to look at 3 standard types of radicals. And they're kind of specially chosen to be kind of relevant to what we'll be learning in your kind of first course on integral calculus, which is what we're learning about now. All right, the 3 standard radicals are the square root of a squared minus x squared, where a is some constant. The other one, the square root of a squared plus x squared. And then the final one, the square root of x squared minus a squared. Throughout all this, this stuff, a is some constant. All right, now each of these radical expressions has its own unique trigonometric substitution we make. And that's because each of the interior quantities to the radicals resembles a different Pythagorean identity. Now, I'm writing right below here so you can match up the basic structure of each inner part of the radical with the appropriate matching trigonometric Pythagorean identity. So maybe pause the lecture to let that sink in so you can see the correspondence. And let's get to the details of how this will work. There are a lot of details. We'll be taking our time to kind of look at everything in this first part of the lecture and then have a lot of the examples in the second part. All right, so let's kind of summarize. These are, kind of good things to copy down in your notes just to have handy when working on questions throughout this lecture and questions in the textbook from the homework. Okay, so for the first and simplest radical, the square root of a squared minus x squared, we make a simple trigonometric substitution. This is kind of like the intro example we saw where it was the square root of 1 minus x squared. But now, since there's an extra constant, a squared inside, we need an extra factor of a in our trigonometric substitution. So here we'll choose x equals sine theta. The differential, which we expect with substitutions, if we make a substitution for x, we have to calculate the differential dx, which would come out, the derivative of sine would be cosine. So dx here is a, that constant, times cosine of theta, d theta. All right. Now, I want to point out, since there's a kind of duality to the basic Pythagorean identity, it is possible for you to make the trigonometric substitution to this radical alternatively as x equals a times cosine of theta. That will mathematically work. But I will say, in teaching Calculus 2, x equals a cosine theta is not the standard choice. The reason for that, calculate the derivative of cosine, it comes out to be negative sine of theta. And the differential is slightly more complicated, that extra negative. And for that reason, we revert to the standard substitution here instead, x equals a sine theta. Both substitutions, a sine or cosine, will work, just that there's preference for the sine substitution since there's no extra negative in the differential, the derivative. All right. Now I want to point out in detail how we use that substitution to eliminate the radical. Pause the lecture and see if you can complete the details. We'll check in about a minute. All right, let's go through this step by step. This is arguably one of the more important aspects of problems involving trigonometric substitution. Our goal, recall, is to eliminate the radical. So let's plug in our substitution. Be careful with order of operations. We have x as a times sine of theta. And since we're squaring x, we square each factor, a as well as sine of theta. All right. And then the kind of the biggest algebraic trick is we factor something out within the radical. And notice each term in the radical has a factor of a squared. So we'll factor that out, but it's factored out within the radical, the square root. And notice now, by factoring a squared out, we have an expression for which we can apply a Pythagorean identity. 1 minus sine squared equals cosine squared. And that basically shows you all the key steps to how the radical is eliminated. Notice here, before we advance, we can get rid of the square root because everything inside the radical is a perfect square. So the radical is now eliminated. So we've rewritten the square root of a squared minus x squared here as a cosine theta by making the trigonometric substitution x equals a times sine of theta. All right, now I want to admit I'm being mathematically a little sloppy. There's some issues with canceling the perfect square inside. Quantities should be positive and non-negative for this to work. That's a bunch of mathematical details which I'll admit are not terribly important. So there's some domain restrictions for the angles, typically like negative pi over 2 to pi over 2. But honestly, in my opinion, they're not that important. All right. So this was all on how we eliminate the radical. Now there was a second part in that table which we left blank, something about a triangle. All right. How in the world will a triangle come into this? Now this is going to be necessary, or one approach, to doing the conversion after we fully evaluated integrals and everything, converting back in terms of our original variable, which is here x. There's two standard ways you can do this. One is with a triangle, sometimes called a reference triangle. The other approach for doing the conversion back to x requires knowing a bunch of trigonometric identities. So I find most students in Calculus 2 have a good foundation on basic trig, basic SOHCAHTOA, but they kind of have forgotten some of the basic trigonometric identities. So I'll advocate for using the triangle approach. Now, how do we create the triangle here? Well, let's take a look at the appropriate trigonometric substitution for this radical. The square root of a squared minus x squared, we make the trig substitution x equals a sine of theta. Now think back to your foundations of trig. trig functions were something about ratios of side lengths of right triangles. So let's see if we can manipulate this to get kind of a basic statement. Sine of theta, recall from SOHCAHTOA, sine of an angle is the opposite side over hypotenuse. So here we can solve for sine of theta. We've expressed it now as the ratio x over a, and we're going to identify that ratio x over a as being the opposite side divided by the hypotenuse. So let's draw a right triangle. Trig's all about right triangles, not about unit circles, sorry. So we draw our basic right triangle, put the angle theta usually in the lower left angle there, and then we label our sides accordingly. Relative to that angle theta, the opposite side is of side length x, and the hypotenuse is of side length a. Now there's a third side missing here. Pause the lecture and see if you can solve for that. We'll check in about a minute. All right, now given two sides of a right triangle, how do you solve for the third? The Pythagorean theorem. And if you do that, you should get that that comes out to the square root of a squared minus x squared. No coincidence that that is exactly the radical expression that we were looking at. That typically always happens. Now, just in case the details might have escaped you, maybe you got stuck, hopefully not, to solve for that missing side length, which we'll label L, there's the work for applying the Pythagorean theorem. All right, so that is how we create the triangle, which we're going to use usually as the very last step to convert our answer for the integral from thetas back to the original variable x. All right, so maybe pause the video, copy this work down if needed. Let's fill in our table from the previous page. We have our radical, we have a matching appropriate trigonometric substitution, and then the trigonometric substitution dictates and creates the triangle here. All right, now for the other two radical expressions, there's just a different substitution corresponding to a different Pythagorean identity and a different triangle. So for the middle radical at the top of the screen, the square root of a squared plus x squared, well, because that matches a Pythagorean identity of the form 1 plus tangent squared equals secant squared, we make a substitution, x equals a tangent theta. All right, we calculate the differential as a secant squared. And it's a little more work, but I encourage you to try it. The only thing we need to know here is that tangent from basic SOHCAHTOA, tangent is opposite over adjacent. So make sure you can complete that work to see where the triangle comes from. And then for our third radical, the square root of x squared minus a squared, this one's a little trickier. Hopefully you see why at the top of the screen on the far upper right corner, why we make the substitution secant. It's because of the Pythagorean identity, secant squared minus 1 equals tangent squared. So for that radical, we make a substitution, x equals a secant theta. We calculate the differential, a times secant theta tangent theta. That's the derivative of tangent. And we have the d theta there. And this is just a little bit more work to create the triangle. Now, I always like to think basic SOHCAHTOA refers to sine, cosine, and tangent. Secant is a reciprocal of one of those, the reciprocal of cosine. So if secant is x over a, cosine is a over x. So just basically reciprocate that. So now you can fill in your sides and then go from there. All right, so make sure you're comfortable with all of this. The radical, why we make that appropriate trig substitution is because of the Pythagorean identities in red at the top of the screen. And also make sure you're comfortable creating the triangle. All right, I realize this is a lot, a good amount of algebra involved, a lot of trig, but this is all so that we can properly eliminate the radical. All right, this I would definitely recommend to pause the lecture and copy this down into your notes. That way you can have that for reference when going through examples within this lecture and also from the homework. All right, let's proceed. I think at this point, we're ready for our first real example. 26 minutes in, and there's been no examples yet. Again, I try, when appropriate, to kind of make sure you see all the background information needed without so much just being spewed at you. So hopefully everything prior to this was informative. Now, with everything we went through, let's see if we can pull it all together for example 1. All right, now there's some steps here, most of which we kind of already went through. The radical here, you can match to one of the 3 standard radical expressions. So the first step, determining which substitution you make, x equals sine, tangent, or secant. Those are the standard 3, that's it. That comes from the radical expression. The second step, plug in your substitution to eliminate the radical. We covered that previously for the radical of the form square root of a squared minus x squared, intentionally leaving some of the details for the other radicals for you to try. The third step, evaluating the resulting converted trigonometric integral that we get. Recall, we're given an integral involving radicals. The appropriate trigonometric substitution converts to a trigonometric integral. So we covered pretty much everything we need in our previous lecture on trigonometric integrals. Obviously, you know that perfectly at this point. So go back and review if needed. And the only new part that we really haven't looked at is converting back to x using the triangle. Now, if you feel like you understand how all the pieces in steps 1, 2, and 3 work, pause the video and give this a try. But I realize for many students, there's just a lot of detail, so it might feel overwhelming. So we'll check in several seconds, allowing those of you that want to pause and attempt this the chance to do that, but we'll proceed. All right, let's get into it. Maybe you made an attempt. Maybe you just feel overwhelmed with all the details, which I certainly understand. Let's go through this together. The first part is how we choose the appropriate substitution. Now, the only thing we need to look at within the radical, or the integral, is we only need to look at the radical, the square root. The square root is of the form x squared minus 1. All the 3 radicals involved x squared and a squared in some combination. And just think, what squared is 1? 1. So we identify little a here as 1, since 1 squared equals 1. And we make the trigonometric substitution, x equals 1 times secant theta. X squared minus a squared requires a secant substitution. All right, we calculate the differential as the derivative of secant, secant theta, tangent theta, d theta. And then the work just requiring a kind of a non-obvious Pythagorean identity, secant squared theta minus 1 is tangent squared. And that work eliminates the radical. So that's pretty much step 1 and 2. All right, we can plug all of these quantities in to our integral. Notice we have kind of 3 different things. We have in the denominator x squared. we have the square root of x squared minus 1, and we have the differential dx. All three of those get converted with the pieces on the left. X squared would become then secant squared. The radical we eliminated to tangent theta. And then the differential dx, well, that just is secant theta, tangent theta, d theta. So we just plug in all of these pieces once the radical is eliminated, and what you should get is some sort of trigonometric integral, which you can see here we do. Now there's a whole wide variety of different approaches required for the resulting trigonometric integrals, but here we went with one that actually requires very minimal work to evaluate. Now, if you got stuck earlier, pause the lecture from here and maybe see if you can complete the problem. Simplify all the trig quantities first and see if you can evaluate the integral. It should be rather simple. We'll check in about a minute. All right, let's go ahead and complete the problem from here. You can probably see that a factor of tangent cancels out in the integral. You have secant theta, but secant squared theta in the denominator, so you can cancel out a single factor of secant. Overall, you're left with the expression 1 divided by secant theta, and, well, crap, that looks really complicated. Now recall some of your tricks for the oddball cases of trigonometric integrals, ones that weren't powers of sine and cosine and weren't either powers of tangent and secant. Well, one of the tips and tricks was to convert everything to sine or cosine. And here, that is actually pretty straightforward. Secant and cosine are reciprocals. So this just simplifies to cosine theta. And cosine has a very simple antiderivative, sine of theta. So the integration goes really quick. The only new part is we need to convert sine of theta back in terms of x. Now this is probably the first legitimate new part to this lecture, since we haven't really seen in detail exactly how we use the triangle to convert back to x. So what you can do, use your substitution, x equals secant theta. Rewrite that as secant theta equals the ratio, the fraction x over 1. Recall you can always write here x or a number as that number over 1 to convert it to a fraction. And because I'm lazy and I just want to use basic SOHCAHTOA, I rewrite secant and reciprocate to get cosine. Basic SOHCAHTOA applies to cosine. So if secant theta equals x over 1, cosine of theta reciprocates to 1 over x. Now we can apply basic SOHCAHTOA. Cosine, we're going to view it as adjacent over hypotenuse. So relative to our angle theta there, the adjacent side length is 1. The hypotenuse has length x. You can work out with the Pythagorean Theorem, the missing side there, but it's always going to be the radical expression. Notice here our radical was the square root of x squared minus 1. Now how we use our triangle here is again with basic SOHCAHTOA. We are trying to convert sine of theta back in terms of x. Pause the lecture and see from your right triangle here if you can determine from basic SOHCAHTOA what sine of theta should be in terms of x. We'll check in about 30 seconds. All right, so again, we're just going to rely on basic SOHCAHTOA. Sine of an angle, sine of theta here, should be the opposite side divided by the hypotenuse. So if we use our right triangle, we get sine of theta as the square root of x squared minus 1, that's the opposite side length, divided by the hypotenuse, x. So sine of theta is the square root of x squared minus 1 divided by x. We plug that in to the last line of our calculation there and convert sine of theta back to x, and that completes the problem. Now there's a lot of details here, given the radical choosing the appropriate trigonometric substitution. There's the step of doing the work for eliminating the radical. There's the step of plugging all this stuff in and getting a trigonometric integral, which you hope and pray simplifies to something nice. And then you evaluate the resulting trigonometric integral. Feel overwhelmed yet? These are probably one of the more complicated topics for students and examples in Calculus 2, since there's so many different steps. But take your time, make sure you understand the details within each step. There's not a ton of variety to the work being done. All right, so that basically completes example 1. Kind of all the following examples we're going to save for part 2, which will start right after this.